Okay, let's start with this one. All right, so let's do modeling. I guess I don't need that. Let's just do exam one review. All right, so for exam one review, there's gonna be a couple of things that you're gonna have. You're gonna have a mix. There's gonna be a mix between, I'm gonna try to write fast. By the way, I write in cursive. If you don't like cursive, I don't know. I cannot write it anything other than cursive. But yeah, it's gonna be a mix between conceptual and problems, and like problems that are gonna have multiple parts. And I want to elaborate on this. But the first thing that you want to know that, and this is kind of like a compilation of questions. I'm gonna go through this and I'm gonna try to talk about the topics. But the first thing is this pertains to numerical errors, and this is going to be the main source of errors. So what are the main sources of error? The main sources of error are all numerical computations. There are two types of error. The first one is the round-off error, and the second one is going to be the truncation, when you truncate an infinite process. Now, round-off error, I'm going to just give you like a quick example. Round-off, an example of round-off error will be due to the finite accuracy on the computer when you want to store, like for example, storing a real number. Like if you want to store a real number in the computer, something like 0.32, if you want to store that in a computer memory, if this 0.32 is like, it has a bunch of decimal places or something like that, like if you try to store pi, if you try to store any sort of like very convoluted real value that has a lot of decimals, and even if it has a little bit of decimals, the computer cannot store this correctly in the computer memory. So the computer will approximate it, and then once it runs out of memory, because it's kind of like in your calculator. In your calculator, when you go, oh, what is this divided by this? And you get this bunch of values. And then you go like, okay, I'm just gonna round it to 4 decimal places. And then you keep using that rounded number and you round the new result, and that's round-off error. You're supposed to use everything on your calculator. But even your calculator has a limited space. Like not everything that you see on your calculator, that's the correct answer. That goes on forever. But your calculator, just like a computer, has to round it at some point. So that's what happens. When you store a real number on the computer, you incur a round-off error because the memory of the computer is limited. There's limited memory. Therefore, when you try to store a real number, it's going to have to round it, and that puts round-off error on your calculations. And then truncation. So truncation error is ending, and this is not supposed to be a capital, ending an infinite process. Sorry, I write so slow. I'm writing on a drawing board and I'm not really used to it. So ending a different process, and the best example is the Taylor expansion. So the Taylor expansion is the perfect example of this. When you're doing like if you watch my video of finite difference approximation, just go and watch the video finite difference. And in this video, what I do is when you're doing finite difference approximation, you do the Taylor expansion. You have like all the different degrees, like F prime, F double prime, F3 prime, like all of these different things. And then you kind of like chop it. You just, you go right after the second derivative and you just cut that process. You just say, cut it, you don't round it, you don't do anything, you just drop all of that information. So if you look at the formula sheet like this guy right here, the finite difference, this is the equation that we come up with. And that's an equation that is omitting information. Like we don't take into account the higher order terms, what we call the O notation and like all the delta and everything, because Taylor polynomial said Taylor expansion is an infinite process. It never ends. So we just say, okay, I'm gonna cut it right here, and I'm gonna not pay attention to any of that information. That's called truncation error. So truncation error arises primarily not because of computers, but because of the kind of like mathematical assumptions that we have to make when we come up with these ideas. We have to say, okay, I don't I cannot represent infinity on a computer. The computer doesn't understand by me saying something is infinite, it doesn't understand it. Like if I'm talking to you and we're talking in the terms of calculus and I'm explaining to the limit to you and I go, oh yeah, we just take delta and we make it infinite small, like it just goes to zero or something, like all this abstract bullshit that when you go to a computer, the computer doesn't understand it. So there are certain assumptions or certain maneuvers that we have to make in order for the computer, for us to be able to create an equation that we can put in the computer. So this equation right here, this has truncation error. The way that we can reduce this truncation error is by reducing delta x, because it's proportional. The truncation error is proportional to the step size. So if we make the step size small, that will reduce the truncation error. However, due to the finite accuracy on computers, if we make delta x too small, we're going to start increasing the round of error, which is what we saw in project 1. In project 1, the error was going to 0 to 0 to 0 because we're reducing truncation error. But at some point, we made it so small, we made the delta so small that the round of error started creeping back up. So it's always a play between these two guys. At least for finite difference, it's a play between those two. Every method is different and every approximation is done in particular ways. But these two guys, you have to know them. The kind of question that you will get on the exam is, what are the two main sources of error? And this will be like the basic, just round of error and truncation. But then they might ask you details like, due to the finite accuracy on computers, if we want to store the real value something on the computer, what kind of error will we have? And then you have to know that will be round of error. Or if they give you an example, they say if we are performing the Taylor polynomial expansion and we halve or we cut or we chop the infinite process, what kind of error is this? Then you know it's truncation error. So there may be more than one question related to error. I'm just trying to figure out the overall what?
So on project 1, what part of it was truncation? What was round off on that table we were given?
What table? Are you talking about the quiz?
No, on the project 1, when we had it solved, we had one table for all of error.
There was no truncation. The truncation comes from the mathematical derivation. We can talk about that during office hours. I can explain how that prevails. But it's not, once you do it in the coding, the truncation is already done. You can think of it that way. We're not including the truncation error on the code. We're simplifying it a lot. But anyway, the next thing that you want to know is you have to know how to convert. So how to convert base 10 to base 2. And what this means is how to go from decimal to binary. And it could be one way or the other, like this how to go from decimal to binary, how to go from binary to decimal. If you're studying for this, if you're practicing this, please, for the love of God, don't go, oh, what is 8 in binary? Like what is this in base 2? Like, don't do that. That's extremely easy. If you're gonna do an example, do something like 32.32 if you want. Like, what is this in binary? Because then you have to break the numerical part, like the number before the dot and the number after the decimal point. Like, you have to break them into two parts. There are different algorithms for doing this. There are different processes for you to go about this, different equations for you to solve this. And go online and pick the one that you like the most. Like the one that he explains in class might not be the most appropriate. Like, I didn't like how they do it in class. I really like how when I took computer science 1, that they did it in a different way, how they did it by hand and everything. So it depends on you. You can also use your calculator. So if you don't want to learn how to do it by hand, you don't really, at no point in your life, you're going to be using this. But if you want to learn how to do it, it's always a good idea to know how to do it. Pick your poison in the case of how you're going to go about this. But definitely try values that are complicated. Try real values. Try values that have decimals, because that's when it gets very complicated. You're not going to take number 8 and put it in binary. Like, that's extremely easy. That's not something that we want to see. But yeah, again, as I mentioned before, the process of storing a real number, now talking again about real numbers, the finite accuracy on the computer, you're going to incur numerical error. Now, another thing I want to talk about is how to represent. So how to represent 0 or I'm gonna say the limits, not like a limit from calculus, but like the largest values that we can use, how to represent zero or the limits. And this is for real numbers, for real numbers. So what I'm trying to say here is I'm going to create two categories. I'm going to say this is single precision. And again, all of this is not for integers. This is all for real values. This is for real. So this is the important thing, real numbers, because those are two completely different sections. So single precision, and I think you guys had this on a quiz. So for single precision, I'm going to have something like this, where I am going to have that these are two, you can think of it as kind of like two categories, two realms, which this is like the negative values. So these are the negative values and these are the positive values. And so zero, the number zero will fall right here in the middle. The problem with real values and the problem with finite accuracy of computers is the number zero cannot be represented exactly. You cannot store zero on the computer. Like the computer doesn't understand zero, what it means. That's why when we define tolerance, it's like on the code, when I say, oh, set your tolerance to 10 to the negative 3, it's because I'm saying, hey, go up to like this point, 1, 2, 3, like go up to like this point. Or if I say 10 to the negative 6, it's like 0.0000001 or something like that. Like those are the accuracy of the computer, but it's because this is how I will have to represent zero. Like if I wanted to represent zero, I will have to represent it that way. I cannot just say, hey, when this function is equal to zero, because the computer doesn't understand it. Now, if you're using something like Octave or MATLAB or anything like that, every time you type zero, the computer just knows, okay, this is very small. It doesn't necessarily know that you're saying, hey, this has to be equal to zero, but it's just some form of approximation to the value zero. And I don't know why can I put it here? Oh, there you go, perfect. I have to use the hard eraser, not the soft eraser. Miss me with that bullshit. That's not right. Anyway, so the way that I will represent this is if I want, and the kind of question that you will get is, how do you represent the zero in single precision? So zero can be represented two ways. On the positive side, you can represent it as 10 to the negative 38. And on the negative side, you can represent it as negative 10 to the negative 38. That will be, any of those two are correct. In the exam, you will probably get one or the other as an option. You're not gonna get both, but they're both correct representation of the number zero in single precision for real values. If you wanted to pick the largest positive value in single precision that you're allowed to use on the computer, that will be 10 to the 38. And the largest negative value in single precision, negative 10 to the 38. So that will be, this is in single precision. Now in double precision, and you might be wondering which one they're gonna ask you. I'm covering both because I really don't know which one they're gonna ask you. They could ask you in single precision or in double precision. And in double precision, if you want to represent the number zero, it will be either negative 10 to the negative 308 or 10 to the negative 308. So this number is super small. This is like extremely small. And the largest value that you can type in double precision is 10 to the 308. And the largest negative value that you can type in double precision, is negative 308. So it's very important that you know this table. You're more than welcome to have this table at hand during the exam, or just memorize it, write it down somewhere. I mean, I'm not your parents. I'm not gonna walk into your bedroom and be like, hey, you're a disappointment to the whole family. I don't know what you're doing during the exam, so I don't know if you're taking it as a group, if you have your notes, if you have 5 computers open and MATLAB and everything. Like, I don't know, I don't care. But definitely have this in hand if you don't want to memorize it. How do you represent zero? You represent it like this or like this in single precision, like this or like this in double precision. What is the largest value that you can represent in single precision will be this. What is the largest value that you can represent in double precision will be this. And again, it depends if they say what is the largest negative value, then it will be this. These two guys. If they say just what is the largest value, then it's just the positive. Just assume that it's the positive.
Rodrigo,
What?
how come during your code you don't ever set the tolerance to these?
I never what?
You never set the tolerance to like 10 to the negative 38 or anything like
So
that.
those are theoretical values. And we don't need it to be like that. Like if you set it something, these are all like theoretical values. Like MATLAB, the maximum that it will let you is 10 to the negative 16. If you recall from project 1, that's when machine epsilon hits. So it all depends on the architecture of your computer, and it also depends on the program itself. There are certain things that you're allowed. So certain things are still nowadays change between machine to machine, but these are all theoretical values based on architecture. Reality is, once you go out in the field, you're going to notice that a lot of things that you learn in school don't necessarily hold true in the field, because all of this stuff is theoretical. Once you go out there, you're going to find out that not everything's correct. But another thing that you want to know is what is machine epsilon. So what is machine epsilon? And we saw from MATLAB that machine epsilon was approximately what was it, 10 to the negative 16 for double precision. And they're not gonna ask you for the value exactly, they're gonna ask you for the definition. But the definition is kind of long, so I'm not gonna write it down, but I will say it. Machine epsilon or machine precision is the smallest value that you can add or subtract from 1 and still be able to tell a difference. Like you're still able to tell a change. Because what happens is, as you saw, once you reach machine epsilon, your value becomes 1. Like whatever value that you're working on, it becomes 1 or it becomes 0. And even if you're adding or subtracting things from it, doesn't change at all. You get the same answer. That's why in project 1, at some point your x's started giving you like 1, 1, 1, 1, 1. Like you just, they had no change because you achieved the point of machine epsilon. But the definition of machine epsilon and exactly how you will see it on the exam is the smallest value that you can add or subtract from 1 and still be able to tell a difference. So that is what I will say. It's very important. Another thing that you will see, and I don't know if I have enough room here, but you have to make sure you understand. And this is what all of these guys have been conceptual questions. This is kind of like when it starts becoming more of a okay, it's not a conceptual question anymore. You have to know the finite difference method. So the and I missed one, finite. The finite difference. You have to know the finite difference method. And what the finite difference method, the way that it's going to be given is we will most likely give you like a table, something like this, like f and f of x. And you're going to be given multiple values like 0, 1, and 2. And here you're going to be given like 2, 4, and 6, for example. And if I say, hey, I want you to find f prime at x equals 1. So right at this point, I want you to find the derivative of f, the derivative of the function f and evaluate it at the point x equals 1. So if I want, and they will tell you how, like they will say, use forward, for example, use forward finite difference, like to do this. And what you're gonna do is, if you look at the formula sheet in here, you can see the equation right here. That's the equation for backward. You have the equation for central, and you have the equation for forward. So the way that you translate this is you have the function evaluated at the point of interest. X is like the point of interest. So if I tell you, I want the f prime when x is equals to 2, wherever you see an x, you're gonna put a 2. And the delta x, I will explain that in a second, but this is the equation that I'm gonna be using. So my delta x is like the step size between one of the x's to the next x's. So this is delta x, this is delta x. To go from 0 to 1, what is my delta x? 1. To go from 1 to 2, what is my delta x? 1. It's always the same. So delta x is equal to 1. So what I'm gonna do here is I'm gonna say, okay, I know that to approximate my thing using forward finite difference at a point x, I'm gonna have fx plus delta x minus the function evaluated at that point divided by delta x. So if I want to approximate it at x equals 1, so at x equals 1, then this is gonna be f evaluated at 1, which is the x, plus the step size, which is 1, minus f evaluated at 1 divided by 1. And if you like do this thing, Like this calculation, this is f evaluated at 2 minus f evaluated at 1 divided by 1. F evaluated by 2, I'm going to write it down here. F evaluated by 2, what is that? The value of f evaluated at the point 2, that's 6. And then minus f evaluated at the point 1. The point 1 is here, that's 4. And then divided by 1, I don't need to put that, so this is going to be 2. And that will be your solution. So it's literally looking at a table, understanding the values that you're given, and using those values in the approximation. You're given the equation. So you have the equation, it's just know how to use them. And if somebody needs more examples like that, I'll be more than happy to provide you some examples during either office or what?
What if the step size between each of them is different? It's not constant.
They will always be the same.
Okay.
You remember from project 1, we defined a variable called delta x or delta. It was always the same. I mean, it changed in project 1, but just because we were trying to prove a point that if you make it too small, you're gonna run into numerical errors. But normally the delta stays the same. So yeah, just make sure you know about that. Let's see. Okay, then now the next thing that I want to talk about is I want to talk about root seeking method. So before I move into that, again, real values and integer values. Know the difference between those two. Integers values are stored exactly in the computer memory. Real values are not stored exactly in the computer memories. That is something that you learn in like intro to C or something. What's the difference between integers and float values, or float? I think it's called floating point operators or something like that. But yeah, Octave and MATLAB, they call everything double precision. So they call everything a double, and that's how they use it. So they never use integers per se. But just know the difference between those two. Now I'm gonna move into like what I consider to be the core part of are. Can you fuck off? Okay, there you go. I'm gonna talk about the root seeking methods, and that doesn't look like a root. Give me one second. I'm gonna talk about the root seeking methods. And there are 3 guys that you have to know in this thing. You have to know bisection method, which we didn't do a project on, but you still have to know it. So you can imagine it's gonna be on the exam. If you didn't see it on a project, it's on the exam. Bisection method, Newton-Raphson. There's the Newton-Raphson. And the last one is secant. So you also have the secant method. So these 3 guys, they do the same thing. Like they literally find the point where if you have a function like this, if you have an x and an f of x here, or I'm not gonna name that axis. I mean, yeah, this f of x here, and if you have a root like this, they literally all are interested in finding this point. What x is this? So they want to find the x value such that when plugged into the function, this function goes to 0. Like that's literally what they want. They want to find the x value such that if I put it into the function, my function is going to be equal to 0. I should not say it goes to 0. I should say equal to 0, but you get the idea. So they all 3 methods, they do the same. And these methods are, if you look at the formula sheet, they're given like how to do them, how to do each of them, how to like the process goes. The process is extremely easy. Once you figure it out, once you read the instructions either here or if you Google how to do them, or you watch the videos from Numerical Methods Guide on YouTube, or maybe if I put the video of how to do it, these things are very easy. Bisection, secant method, and Newton-Raphson. It's like a process that you just do it and repeat it, do it and repeat it, do it and repeat it. Like it's extremely straightforward, but there are certain things that I want to talk about. So I'm not going to necessarily tell you how to do this. I think this is something that you should be able to figure it out on your own. It's very easy. But I do want to talk about something that is called the residual and iterative convergence, because you're going to have questions that pertain to this. So you have the residual. You have that's not how you spell it. You have residual and you have iterative convergence. So iterative convergence. And this applies to all. That's how it sounds like it says applies to all. That applies to all of them. So what I mean by this is that equations that I'm going to use to label residual and the equations that I'm going to use to label iterative convergence, they're going to be the same. So I'm going to use the same graph that I have right here. So let me just delete this real quick. And whoop, there you go. All right. So if I have, let me change the color. If I have my graph like this, if I pick an initial guess here, I'm going to pick x sub 0. If I evaluate that point x sub 0, if I evaluate it in my function, I'm going to get the value f at that point, x sub 0. Now, one thing that I'm going to notice, and this is normal of this sort of algorithms, like if I wanted to implement the algorithm of the Newton-Raphson. So Newton-Raphson looks something like this. N plus 1 equals xn minus the function evaluated at xn divided by the prime evaluated at xn. So what this does is this is kind of like a process, and I use Newton-Raphson because it's kind of like one of the easiest to see. What this process is going to do is it's going to use whatever approximation of the root I have before, the evaluation of the root on the function and the evaluation of that root on the derivative. And this is going to approximate, this is going to find the next approximation of the root. So what I'm trying to say is, let's say I want to do it by hand. I want to start and just go for it. So I'm going to do the first approximation of the root. X1 is going to be equal to X0, which is my initial guess, the function evaluated at the initial guess, and then the prime evaluated at the initial guess, right? That will give me that X1. If I want to find my second iteration, my second approximation of the root, X2 is going to be equal to X1 minus the function evaluated at X1 divided by f prime of X1. So I'm using this value right here. I'm using that value there, and I'm evaluating on the function. And I can go on and on to whatever many iterations. This is an infinite process. It never ends. It's kind of like a loop. You use the value from before to calculate the new value. So I need to set up some stopping criteria, which those were the if statements that you had on your code. I need to set up a stopping criteria. So what I'm going to do, and this is very popular of, this is what I'm going to say is the difference of how mathematicians and engineers approach the problem in two different perspectives. So engineers tend to be more of like, I'm going to study the behavior of, and I guess they're similar at the end. I'm going to study the behavior of systems. If I have a pendulum and I see it going back and forth, I can study it and I can predict the motion. I can think about it and I can be like, okay, it's being affected by these forces. It has these material properties, like all these things. And the idea is that we apply the same ideas to study the behavior of the function. One thing that I'm going to notice is as I go down this infinite process, as I go down this iterative process, once I go to like whatever, once I get very close to the value, the correct approximation of the root, one thing that I'm going to notice is the x, let's say at x9, I start converging to the solution, at x sub 10. One thing that I'm going to notice is x sub 7 is going to be very similar to x sub 8, and it's going to be very similar to x sub 9. Like they start, once you start converging to a solution, the value of all your approximations start being very similar. And this is because as you find more and more approximation, like I'm going to go back here to the graph, as I find, like let's say I find x1 to be over here, then I find x2 to be over here. And this is an arbitrary process. I'm not saying this happens for Newton-Raphson or bisection. They all work in different ways, but they follow the same idea. My approximations of the root are going to keep getting closer to the real root. But what's going to happen is all of those approximations, they're going to keep happening like very close. Like you see how x0 starts all the way over there. Then I get x1, then I get x2, then x3, 4, 5, 6, 7. Like they all kind of like start dancing around that point because I converge to a solution, but this is an infinite process. It never ends. So what I'm going to do is I'm going to define something called the residual. I'm going to take this distance y, this distance right here, and I'm going to say, hey, you know what? This distance, which this distance happens to be just the absolute value of the function, because I care about the magnitude. Like that distance is just the an x sub 0. That distance is just the evaluation of the function. But if I care about the magnitude, I'm going to make it absolute value. I'm going to take that distance and I'm going to call that the residual. Why is it called the residual? Because it's whatever is left for me to get to that root. Because remember the definition, if x is a root, so if x is a root, and I'm gonna call it xn, an arbitrary x. If xn is a root, then if I take that root and I plug it into my function, what should I get? I shall get 0. So I call it the residual because it's the distance, the magnitude that I have left for me to reach that point, for me to reach that axis, that x-axis, and make that value, make my function go to 0. I'm trying to drive my function towards 0. I'm trying to go this way. So what I'm expecting is, as I keep finding more and more roots, as I keep finding this, guys, this is the residual 1, residual 2, over here is residual 3. I'm expecting all of those values, all of those successive residual calculations to go to 0. And if you look at your project 2, that's what you observe. When you plot the graph, if you look at your residual graph, it's something like this. It's like it's kind of choppy, but it's going towards 0. As the number of iteration increases, the magnitude of my residual is going to 0. So I can create something, I can create a relation based on this, and I can say, I'm gonna define my residual at a particular iteration. And what this is gonna be is, this is gonna be the absolute value of, not prime, the absolute value of my function evaluated at that approximation of the root. And what I'm expecting is, if xn happens to be the root, is equal to x root, like whatever my approximation, or is very close to it, I'm expecting my residual at that xn to go to 0. But again, we get back to numerical methods. This numerical methods, don't try to think too much of the algebra. Numerical methods, we cannot express 0 as 0. I cannot tell my code, hey, once the residual is equal to 0, cut it. No, I cannot say that, but I can say, hey, once the residual at whatever particular x that you happen to be at is less or equal than a tolerance, that's why we use it in project 2. Once it's less or equal than a tolerance, end the code, break it. You can break out of the loop, you can break out of the process. So this is why it's important. And that tolerance is what we usually define in the code. We say, hey, let this be 10 to the negative 5. So 0.00001. That's what we will call our new 0. That's what we will represent in the computer as the 0. But that's why we use this definition of residual, because if my code is converging to a solution, if I am converging to a solution, if my code is working as intended, which means my initial guess was good, it wasn't shit, and my code is not blowing up, it's actually moving in this direction, it's going towards the root and not away from the root, I'm expecting the residual to go down, because the value of the function that is being evaluated at every single x is going to 0. So my residual has to go to 0. Now, just because I am a perfectionist piece of shit and I like to make sure that things make sense, let's say I want to exploit another characteristic of functions. So another thing that happens and that you can note from this graph is, as I keep getting closer and closer to that root that I have in there, one thing that you will notice is, look at the distance between the x's. This is x initial and my x1, my first approximation of the root. This distance, I'm going to call it epsilon. This is epsilon 1. This distance right here, epsilon 2, is smaller than the first one. And the next distance between x3 and x2, which I'm going to call epsilon 3, is smaller. Then x4, this one I'm going to call between x4 and x3 is smaller than the distance between, and I'm talking about the x-axis. The distance between this guy is smaller. As my code starts converging toward the solution of x, as I keep getting closer and closer towards the solution, the value between each consecutive x, like if I find a new x, which I'm going to call x1, and I have my initial guess, I can calculate the distance between those two. And then once I find x2, I can do x2 minus x1. I can calculate the distance between those two. What I'm going to notice is, as I go down the iteration rabbit hole, eventually the distance between each consecutive x is going to go to 0, because all my x's start kind of like converging towards that particular, the real value of the x. So the distance between them is going to go to 0, because they start kind of like just piling together in the correct value. So I can exploit this by creating something that is called the iterative convergence. So the iterative convergence, the whatever xn plus 1, so like xn plus 1, this is going to be equal to the absolute value of xn plus 1 minus xn. So this is the distance between like all of those x's. And what happens is as x plus 1, as this guy gets closer to the root, like as he gets closer to the root, like the real root, to the root or my approximation of the root, I can expect e to go to 0, or epsilon, I'm sorry. I can expect epsilon to go to 0 because the distance between all of those x's is getting smaller and smaller. So these two definitions, the definition of residual and the definition of iterative convergence, they will be the same for Newton-Raphson, secant method, and bisection. They do not change. They stay the same. We will change them once we get into simultaneous system of linear equation, which are matrices. We will make our own definitions, but these are things that do not change. And you will be asked questions like, for example, you might be asked a question like, what is the initial residual? What is the initial residual? For any of this method, they will just ask you, it will help if I knew how to type correctly, initial residual. So if they ask you something like this, what is the initial residual? Then you can just say, okay, I know that the definition of residual at any particular x is equal to the absolute value of that function evaluated at that particular x. So if I'm talking about the initial residual, it will be the residual using the initial guess. So that means evaluate the absolute value of the function at the initial guess. And that will be your initial residual. If they tell you after, they say after 2 iterations or after 3 iterations, what is the iterative convergence? So what is, I'm just gonna try so what is the iterative convergence? And I'm just shorting out because I'm running out of time. So after 3 iterations, what is the iterative convergence? I know that the epsilon at x3 is gonna be equal to the absolute value of x3 minus x2. So my current approximation of the root minus the previous approximation of the root. So if they ask you for the iterative convergence at your 3rd iteration, it will be the absolute value of the difference between your approximation at the 3rd iteration minus the approximation at the 2nd iteration. That's why it's important that while all of this process, they're very simple, they're very straightforward, like the equations that you're gonna be using, it's very good that you're good at like housekeeping or housekeeping, like keep everything neat, keep everything organized, because the values that you use, you will reuse them. So definitely don't turn this into a whole shit show as you're working through the things. Okay, but anyway, I think this is literally what I have for you guys. So that's the question. That's the kind of questions that you can expect. There's one more thing that I want to talk about, and it's just gonna be quick. So things to know about Newton-Raphson. So Newton-Raphson, and this is just kind of like a recap. Newton-Raphson requires. So this requires, Newton-Raphson requires the function, it requires the prime of the function, and it requires one initial guess. And that initial guess will be x naught, right? Bisection, and I'm gonna type it here like this, bisection. So bisection requires the function and I think in a bracket. So you can think of bisection as required 2 initial guesses. We don't necessarily call them 2 initial guesses. I mean, you can call A and B your initial guesses. There's 2 of them, but we primarily refer to them as bracket, which means if I have something like this and I have an equation and I know the root is here, I'm gonna bracket this. This will be A, this will be B, and whatever the bisection happens, the bisection is kind of like, just do like a cut in the middle. Like the point C is equal to A plus B divided by 2. So I like cut it in this middle, and then I go like, okay, is this guy changing sign? Is this guy, because here, if I were to evaluate this point and this point, they have the same sign. They're both negative. So I say, okay, I'm not gonna use this side. Now this is my new A, and this is my new B. So bisection is kind of like the name implies, it's bisecting. But again, I don't want to go into the methods themselves. I want you to spend the time doing that. But yeah, bisection requires an initial bracket, and then secant method I'm gonna say over here secant. Secant requires the function and requires two initial guesses. And that's gonna be x0 and x1. Now, why does Newton-Raphson only require one initial guess? Because Newton-Raphson relies on the definition of a tangent line. That's why it requires the exact first derivative. Secant method, as the name implies, requires on the secant line, and drawing a secant line between 2 points. That's why it requires two initial guesses. And bisection works completely different than these two guys. Now, the reason this guy and this guy work so similar is because secant method comes from Newton-Raphson. Secant method is Newton-Raphson, but instead of writing the first derivative exactly, we approximate it using the definition of the slope for small enough deltas. And so you may not be tested on the secant method because it's kind of like redundant. So I will primarily focus on bisection and Newton-Raphson. Those will be the two that I focus primarily rather than secant method. It's still a study secant method because it could be on the exam. There is always a possibility. But yeah, that thing with regards to fixed point iteration. But you guys know that fixed point iteration is like if I have something like this, like 2x plus 3, what I do is I solve for x. So I have y minus 3 divided by 2. This is equal to x, and then I call that x. I call it like gy or something. Like I call it a function of this, and then I iterate for when this point is 0. Like you guys know that, right? So it's literally just a change of variables, and then you're finding where that point is 0. It's something like, I don't remember exactly like the iterative thing, like that fixed point iteration, because honestly I never see it, but it will be good to study. Definitely look into that. It's very, I do remember that it was very simple, but I don't think it has any conceptuals other than there's one thing, and it's on the formula sheet. I think it's on the last page. There you go. That for fixed point iteration for any given function, like you rewrite it as like what I just said, you solve for x and you make it equal to gx. This is a statement, and this is always true. If you are doing fixed point iteration and you create your function g of x, the prime of g of x, the magnitude of the prime of g of x has to be less than 1 for all values of x within a certain domain that pertain to a certain domain. What this means is if you solve for your g and you take that g and you take the prime of it, regardless of the value of x, it will always be less than 1 in magnitude. Like the prime of your fixed point iteration should always be less than 1, regardless of whatever value of x you're evaluating it at. But this is more of a conceptual thing. You're not asked this thing on the exam, but it's more of like a conceptual, like is this true or false or something like that. But yeah, that is everything. Here's secant method, Newton-Raphson. This equation right here is important. So epsilon will be your tolerance, and n tells you the number of iterations to reach that tolerance. So b minus a, you're given b, you're given a, you're given the tolerance. You do this equation and it gives you an n value. If it gives you an n value like 15.5, you report it as 16. You report it to the next one. I don't think you're going to have this equation on the exam, but if I remember correctly, you report it to the next one because it's what iteration have you achieved this accuracy. So yeah, if it gives you 15.5 or 15.2 or 15.6, you report it as 16. Root solving algorithms, here's all of them. Bisection, this is bisection. And yeah, and know how to do Horner's method. So Horner's method is just synthetic division. If you know how to do synthetic division, you know how to do Horner's method. As far as conceptually goes, just know that it deflates a polynomial. It evaluates the polynomial at the particular root. And I think it just makes it more efficient. Like it's faster. The calculation when you do it on a computer is faster because you're pretty much taking a third degree polynomial and you're breaking it into a combination of first degrees x's, first variables that are to the first degree. But yeah, that's everything. So yeah, let me know if you have any questions.
So for Newton-Raphson, and those you don't require a tolerance. It's just
no tolerance is only for codes.
Okay.
because we on the exam, we will tell you when to stop. We will say, what is the solution at the second iteration? What is the solution at the third? Like we always specify which iteration we're interested in. So I will say the first, definitely for the exam is supposed to be multiple choice, not fill in the blank. For the exam, I will say the first thing you should do is like usually those two big problems are at the end. Definitely start with those because they take the longest. Everything else is conceptual or short answer.
So for the secant method, since you're given two initial guesses, do you start the iteration on 2 or 1? Since the first one is still a guess.
No, we count when you're doing it by hand. We don't count those as iterations. In the computer, we do, and we shouldn't. But I think we call it iteration one because when you define initial guesses don't count as iteration because you haven't done the process. Yeah. So I will say you start at iteration 1. Once you write down and you obtain a new x, that's your first iteration. Every time you obtain a new x, that's your iteration.
Okay.
All right. Bye.
Thank you. Bye.
No problem.